Assalamualaikum warahmatullahi wabarakatuh. Hello everyone! Today we will show you how to make the molecule shape of chemical bonding. But before that, let us introduce ourselves. We are from group 3. My name is Rahma Safitri and my friends are
Ijayanti Pardosi
and
Cecilia, Yosephin, Sijabat.
So, enjoy this video. Check it out! So everyone, this is our tools and materials how to make the molecule shape of chemical bonding. The first is origami. The second is plasticine. The third is 3 color of pen. The fourth is lidis. The fifth is ruler. And the last is gloves. Okay guys, we will create and draw domain geometry and molecules based on the Phpr concept, and we will also create and draw for its hybrid orbital and molecular from based on the concept of hybridization. But earlier, we didn't forget to thanks to Ma'am Dr. Siti Jahro as our lecturer who have given us the opportunity to perform the engineering activities of this idea. Thank you and welcome. But on this occasion, I will explain the geometry of domain and the molecular shape based on Phpr theory. The shape of a molecule or a geometry serves to describe the arrangement of atoms on a molecule based on the position of a pair of electrons on the molecule, and then the couple of electrons on these molecules may or be a couple of free electrons or a pair of electrons. And then there is a theory that deals with the molecular form or the theory of the Phpr theory. And then Phpr theory is a theory that deals with or forms a molecule based on PAB and PAY at the central atom. PAB and PAY will refuse each other because of its negative load, and the rejection of this occurs in the central atom, thus affecting the molecular shape of a compound. And then in this theory, there are 5 different compounds. The first is linear form shape, where linear shapes have a 180 degree linkage angle, and the second is a flat triangle, which has an angle of 122 degree, and the third is tetrahedral, which has an angle of size 109.5 degrees, and the fourth is the square bipyramid has an equatorial point of 120 and axial bearing 90 degrees, and the last one is the form of the octahedral molecule shape, which has a 90 degree angle. And then how do we determine how to draw or form a molecule based on Phpr theory? So we draw and form a molecule based on Phpr theory we draw on the Lewis structure. As the example for today is, we will consider this time are like CCl4, SF4, POCl3, EOCl3, XeF4, and XeO2 and F2.
Okay, now I want to show you the domain electron of POCl3. So, POCl3 have 4 domain electron, which 1 is double bonding with O and 3 is single bonding with Cl. So, the domain electron in POCl3 is like that. So, this is the domain electron of POCl3. Hybridization of phosphor oxychloride or POCl3 with atom center is P. P have number atom 15, so the configuration is neon 3s2 3p3. So the outer shell of P is 3s2 and 3p3. S has 2 electrons, so orbital S is filled by 2 electrons. And orbital P have 3 electrons, so orbital P is filled by 3 electrons. Now we see there is not enough space for OCl3. So we need to move 1 electron from S to the next orbital is orbital D. So the configuration be like that. We fill 1 electron for orbital D. So now we move to the hybridization. First, we fill the electron. But now we see there is bonding with oxygen is double bonding, so the last electron is not hybridized. So this electron is not hybridized. So now here, after that, the Cl is fill the space. There is 1 Cl, 2 Cl, 3 Cl, and here is O. So we get 1 electron here, 2, 3, and 4. So the hybridization of POCl3 is sp3 with the same name is tetrahedral. Okay guys, now we next to EOCl3. The first, we make the domain electron of EOCl3. As we know, EOCl3 have 5 domain electron, and the shape of domain electron is like this. EOCl3 have 5 domain electron. So, this is the shape of domain electron of EOCl3. And next, now we make the molecule shape of EOCl3. But before it, we change the up of the bonding of the up to be the double bond, because the bonding between the E with the O is double bond. Now we change. And then we put the electron for this bonding. So, this is the shape molecule of EOCl3 as we call tetrahedral or tetrahedron. Thank you.
This is the hybridization of iodium oxide trichloride. The central atom of iodium oxide trichloride is iodium. That is because iodium has more biggest radius atom. Iodium has 53 number atom. So, the configuration is krypton, 4d10, 5s2, and 5p5. The outer shell of iodium is 5s2 and 5p5. In orbital s, there are 2 electrons, so we fill 2 electrons in orbital s. While we fill 5 electrons in orbital p because it has 5 electrons. Because there are no space for chloride and oxygen, we must move 2 electrons from p to orbital d. So, we get after that, one column of orbital d, that is for double bond, so it cannot hybridization. The hybridization occur in orbital s and orbital p. Hybridization occur in orbital s and orbital p. So we get after that, chloride fill the space in orbital p. And oxygen fill the space in orbital d. We can see that one column of orbital d, that is no hybridization, because that is for double bond. So from the result, we can see that the hybridization of iodium oxide trichloride is sp3d, with the shape is trigonal bipyramid. Now, I want to show you how to make the domain geometry, molecule shape, and hybridization of xenon tetrafluoride. In domain geometry, there is no double bond or triple bond. There is only use single bond. So, in domain geometry, we only use sticks or ladies with size 11 cm. First, we must determine the central atom of xenon tetrafluoride. The central atom of xenon tetrafluoride is xenon. Because xenon has most biggest radius atom than fluoride. The number atom of xenon is 54. So, the configuration of xenon is 2, 8, 18, 18, 8. So, xenon has 8 electrons, which 4 electrons of xenon has bonding with fluor, and 2 pair others, it is free electrons. Okay, let's make the structure domain geometry of xenon. This is the domain geometry of xenon. The degrees between each bonding is 19 degrees. So, from this one, we can see and determine the structure of domain geometry from xenon is octahedral. Now, we make the molecule shape of xenon tetrafluoride. It's just put 4 fluoride into each bond. This is the molecule shape of xenon tetrafluoride. Fluoride has bonding with flat angle or side from xenon. So, the shape molecule of xenon tetrafluoride is flat rectangle, or in Indonesia, we say segi empat datar. This is the hybridization of xenon tetrafluoride. Xenon tetrafluoride has central atom that is Xa, where the number atom of xenon is 54. So, the configuration of xenon is krypton, 4d10, 5s2, and 5p6. The outer shell of xenon, that is 5s2 and 5p6. So, the orbital of xenon, that is s and p. S has 2 electrons, so the orbital of S, that is filled by 2 electrons. P has 6 electrons, so the orbital of P that is filled by 6 electrons. There is no space for fluor, while fluor will fill for the orbital. So we need other orbital, that is the orbital. After that, we fill the electron. To make the space for 4 fluor, we must move 2 electrons from orbital P to orbital D. After that, hybridization occurs. So, the orbital be like that. So, after that, fluor fill the space. 1, 2, 3, 4. So, we get 1, 2, 3, 4 electron. So, the hybridization of xenon tetrafluoride is sp3d2 with the shape is octahedral. Now I want to make the domain geometry, molecule shape, and hybridization from xenon dioxide difluoride. Same with xenon tetrafluoride, xenon dioxide difluoride has central atom that is xenon. Xenon has 8 electrons, which 2 pair electrons has bonding with oxygen, and 1 electron has bonding with fluoride. Xenon has 5 domains, which 2 pair electron has bonding with oxygen, 1 pair electron has bonding with fluoride, and 1 pair is free electron. So let's structure the domain geometry of xenon. This is the domain geometry of xenon. We can see the shape of domain geometry is trigonal bipyramid. Now, let's make the molecule shape of xenon dioxide difluoride. Before, we change the top and below bonding because between oxygen and xenon, there is double bonding. This is the molecule shape of xenon dioxide difluoride. The name of this molecule shape is siso, or in Indonesia we say jungkat-jungkit. The hybridization of xenon dioxide difluoride same with xenon tetrafluoride, where the central atom is xenon. Xenon has the out skin is 5s2 and 5p6, so we fill the electron. Because there is no space for oxygen and for fluoride, so we need the other orbital, that is d orbital. So we fill the electron. We move 3 electrons from orbital p to orbital d. So we get the 2 space that is for double bonding, and the 2 space that is cannot hybridization. Orbital s and p, that is occur hybridization. So the electron, like the space will fill by fluor and oxygen. Because the 2 space is not can hybridization, and that is for double bond, so the hybridization of xenon dioxide difluoride is sp3d with the shape tetrahedral.
Now, I want to show you the domain electron, hybridization, and molecular shape of SF4. But before it, SF4 have domain electron is 5, with 4 bonding with F and 1 electron free, or free pair electron. So, the first, let's make the domain geometry of SF4. SF4 have 5 domain electron, so the shape is like that. So, this is the domain geometry of SF4, or we call is bipyramidal trigonal. Now, let's make the molecular shape of SF4. How to make it? We just make the electron in the lattice or stack. So, the molecular shape is like that. This is the molecular shape of SF4. Here is place or shape for free pairs electron. So, from the molecule shape of SF4, it called its tetrahedral. This is the hybridization of sulfur tetrafluoride or SF4, with atom center is S, where the number atom S is neon 3s2 3p4. So, the outer shell of S is 3s2 and 3p4. So, the orbital of S is S and P. S has 2 electrons, so we fill 2 electrons to the orbital S, and P have 4 electrons, so we fill 4 electrons for orbital P. But now we see there is not enough space for F, so we need to move 1 electron from orbital P to orbital D. So the configuration be like that. Here, 1 electron for orbital V move to 1 orbital D. So the hybridization is occurs. Now, we fill the electron to the hybridization. After that, F fill the space. There is 1F, 2, 3, and 4. So we get 1 electron here, 2, 3, 4. This is the orbital S, this is the orbital P, and this is the orbital D. So, the hybridization of SF4 is sp3d with shape of hybridization is trigonal bipyramidal.
Okay, next, the second one, I will make the molecular shape form of SF4, and this is the first plasticine. Along with the plasticine that will be formed, and this one is the first one, is formed into a larger sphere to make the central atom of S. Okay. Here the result, and then as well as the result of this information, then we insert the lidi into the symmetrical plasticle in the right side and the left side, in the up and the below with the same place. After that, we hold the smaller atomic F4, but before that, with the other plasticine, we make the other circle more smaller than the first one, and after that we insert it to all the lidi.
This is the hybridization of tetrachloromethan or CCl4, with the central atom is C, where the number atom of C is 6, so the configuration is 1s2, 2s2, and 2p2. The other cell of C is 2s2 and 2p2. So the orbital of C is S and P. C has 2 electrons. So the orbital of S that is filled by 2 electrons. P has 2 electrons, so the orbital of V that is filled by 2 electrons. So this is not enough space for Cl, while Cl will fill the orbital. Let's fill this space for so to make the space for Cl, we need to move 1 electron from s orbital to p orbital. So the hybridization occurs. So the orbital be like that. After that, Cl fill the space. 1, 2, 3, 4. The hybridization of tetrachloromethan is sp3, with the space name is tetrahedral or tetrahedral. Okay, my friends, that's our experiment today. We hope you learned something from our video, and if we have made a mistake, we are say sorry. And for the last, we say
Thank you and bye-bye!